Good morning, folks. I did get the quizzes back. I have to apologize. There's I still have a couple of things to work out with the marker. In his defense, I made a mistake because I gave him the marking scheme for a previous version. I changed a couple of questions and I didn't change the marking scheme. The other thing too is students, I want to make sure that we have better communication about part marks. I like to give part marks, and so I have to communicate that better. So in essence, the quizzes were okay, but I want to go through them because I think the marks will be higher when I go through them. The other thing, we do have a quiz today, and I sent some things out last night. One of the things I want you to know, and this is for me, you have to gauge every instructor the same, but in terms of naming compounds, I don't get too concerned about it. So the naming things that I will give you are going to be relatively simple. I don't care about naming really complicated things, but I want you to be able to name things. What is really important is that when you give something a name, you can draw the correct structure of that compound. So, you know, if it's supposed to be bromochloropentane and you put chlorobromopentane, I'm not going to be upset about that because I can still draw the structure from your name, even though you may have gotten the alphabetical prioritization wrong. That's a minor point. The major point is that you got the numbering correct and you can actually draw the correct molecule from whatever name you gave it. And then in going the other way, if you have, I think you'll notice I gave you names and asked you to draw structures today for today's quiz. And I'm more likely to do that because I find students have a much better chance of getting that right. Going the other direction, that's when you get into the semantics, okay? So what's always important for me is that when you give me a name, I can draw the structure that you meant for me to draw. Having said that, that's me, okay? You do have to gauge your other professors. And I think for our department, most of the time, it's pretty good. We don't get too... I've had organic instructors in my past that would mark you wrong. You know, if you misspelled a part, you could be marked wrong. So, anyway, let's talk a little bit about where we are. Last class, we talked about the reaction. We talked about this reverse reaction. We talked about the formation of acetals. And remember, acetals have two alkoxyl groups bonded to the same carbon. That carbon was formerly a carbonyl compound. When we react alcohols with a carbonyl compound, under the right conditions, we can get the formation of an acetal. Again, we want to be aware that these reactions are done under equilibrium conditions when they're done under acidic conditions. This is a complete equilibrium reaction. So if we wanted this reaction to go, we would probably, we may use the alcohol as solvent if that's convenient, and if it's something like ethanol, that would be convenient. It could be a bigger alcohol that's not a liquid and not or expensive and is not as convenient to be a solvent. Then we would use an organic solvent that we are able to keep dry. We would do the reaction so that we would only get one equivalent of water formation. That means we would probably favor this side. And then we might do things, we might use tricks to remove water as it's formed to drive this reaction to completion. If we want to go the other way, it's relatively easy. We just get everything dissolved up and then we add a lot of water. And we shift the equilibrium because we're adding water to this side. Remember, Le Chatelet's principle shifts the equilibrium and we can form the alcohol. Or, I'm sorry, the ketone, the parent ketone. When we have, this is a case where we have a molecule where we have a carbonyl functional group and we have a hydroxyl functional group on the same molecule. Intramolecular reactions have a tendency to go fairly quickly because when you think about it, if you have intermolecular reactions, molecules have to float around and come in contact with each other. When they're connected, this functional group is connected to this functional group. They can't diffuse away. They're always nearby. And in this particular instance, the product that's formed by forming a hemiacetal, so this will cyclize and we get a 5-membered ring. 5- and 6-membered rings are entropically favored. They're very easy to make. And if you have good chemical models, you can make 5- and 6-membered rings, and you see that they're easy to make. And if you have good chemical models, making small rings and making larger rings are a little bit more difficult. 7-membered rings are actually surprisingly difficult to make. 8-member rings the same. Then when you get very large rings, they can become easier, but there's a lot of conformations. So when we form 5- and 6-membered rings, this is very much favored reactions. So this would go quickly. Notice we're showing this equilibrium favors this side, and that's because it's an intramolecular reaction. And when it goes back, this functionality doesn't have a chance to diffuse away. That's why this type of reaction is favored. And then going from here to here, probably more than one step. Something will float around and remove that proton, and then it'll float back, and when it puts the proton back, it's more likely to put it back there to form here. Okay? That's the other thing you want to remember. Protons are easily moved around within a molecule, not necessarily intramolecularly. Something may have to come along and act as a proton shuttle. Okay? And that's the other thing we want to get used to. We often see this. That doesn't really exist in solution. We don't have naked protons zipping about. In ethanol, if we're in ethanol and we don't have very much water, this is the most likely proton carrier in ethanol. If I were in ether, diethyl ether, if that was my solvent, this is likely to be the proton shuttle. Now, we may have to add a little water in certain instances. If we add a little water, water will act as the proton shuttle. But protons are easily moved about by many different things. All you need to be a proton shuttle is a pair of electrons that are available to grab a proton. Okay? So depending on the conditions, even if it's a weak base, it can still be the base that's picking up that proton if we throw a strong acid at it. So don't worry too much. And we often just say H+ because in a typical reaction, there's a lot of things that can be carrying that proton about. There's water, there's alcohol, even the ketones. We're protonating them. They can, if they're protonated, they're acids, and they're going to give up that proton to something. So don't get too concerned about moving protons around. They're easily moved around. And like I said, we show this like it's one step. We need to, as chemists, we need to realize that's not likely just to jump all the way through there, okay? And this thing actually can't reach a conformation where intramolecularly it easily grabs it. So to get from here to here, something floats in, maybe a water molecule pulls that proton off, and then it migrates over to here and drops the proton off there. That's how our protons move around. Now, this is called a hemiacetal because it has an alkoxyl group. This is from here, this is an OR. Just so happens that the R is connected to the rest of the molecule. And this is a hydroxyl group, so this is a hemiacetal. Hemiacetals are fairly common. Now, I will warn you, this is a very good question to ask. I've talked to you already about the fact that the carbonyl compound is prochiral, that is, it's planar, and attack can happen at either side. We now actually have, if we look at this, this is a chiral center. This is plus glucose. If we throw that in water, if we have pure plus glucose, and this, I don't know if they do this experiment in biochemistry, we could take pure plus glucose, crystallized, dissolve it up in water, and watch as it racemizes between these two. And the question might be, how does that happen? Well, this is just a hemiacetal, just like this is. And it can go backwards. And when it goes backwards, the OH group can attack either side of that carbonyl compound. Now, how are you going to figure all that out? Well, if you were given the question, you were found that this racemizes, what you might want to do is try initially to ignore the rest of these things, i.e. strip them out and see if you can explain how that racemization occurs. And that racemization occurs by this opening up to form the carbonyl compound, and it can open up and close to form the hemiacetal, just like this could, okay? You may want to shift protons around after you've opened it up. So here, you could move this proton over to here, and then you could see that that could be an aldehyde group, and that's your alcohol that opens up. Also, be aware, here's another molecule. Take a look at this molecule. Do we see any hemiacetal or acetal functionalities on this? In actual fact, what about this carbon? It has an alkoxyl group. Has an alkoxyl group. Okay? Same with this carbon. Alkoxyl group, alkoxyl groups. These are both acetal functionalities. However, in biochemistry, you might be told that one is an acetal and one is a ketal. Why is this one different? This is older nomenclature. You guys don't have to worry about it, but I am warning you, you may have to worry about it in other courses. This is a ketal because when you open it up, this functionality, it will become a ketone, right? This will open up, it'll be an aldehyde. There's an H there. Don't forget about those H. So a couple of things that I always see at this point is students forgetting about the H's that are there and we're not drawing, and students not counting their carbons. So for instance, I'm going to do a simple reaction. Actually, I'm going to do it like it was. I'm going to do this instead. So when people do this reaction, we've opened up our ring and we've added, this is what we've added. Okay, but a lot of people, sorry, this should now be, do that, okay? So what they're seeing is they see this and they see these two things and they still see that there, but it's wrong. If you count carbons, 1, 2, 3, 4, 5, I have 5 carbons in my starting material. I need to have 1, 2, 3, 4, 5 carbons in my product. In this case, I have 1, 2, 3, 4. I've lost a carbon. So count your carbons. It's a very simple check. Count your carbons in your starting materials. Count your carbons in your products. And you don't necessarily need to get in the habit of doing that all the time, but in instances like this where it's easy to lose a carbon, be aware that sometimes carbons seem to disappear more easily than at other times. And it's usually with functional groups like that. Cyclic acetals. If we react this ketone with this compound, we have 2 alcohols here. They just happen to be on the same molecule. So the mechanism is exactly the same, and this is a question where we've gone through this mechanism. I might throw this on an exam. We're not going to cover it specifically, but you guys should be able to get there because it's just 2 alcohols. They happen to be on the same molecule. And notice now this thing is connected. We have a cyclic acetal. This is a very common reaction because it provides us with a way to protect carbonyl compounds. Because all we have to do is put lots of water in and we can get back to our carbonyl compound. As it turns out, acetals are stable under basic conditions. So I've put this in here, and when I find them I'll try to do it. These are actually supposed to be negative charges. There's a problem with the PC to MAC conversion even to this day. They don't like to talk to each other. That's what these were supposed to be. Anyway, Acetals are stable under basic conditions. So that provides us with a way of protecting. Acetals are used to protect aldehydes and ketones from undesired reactions in basic solutions. So here's an example. If we wanted to make this compound, right away we see a tertiary alcohol. One of the things we should think about when we make a tertiary alcohol is, I know how to make tertiary alcohols. I can make them from Grignard reactions and a ketone. That gives me a tertiary alcohol. So all I have to do is figure out what would be the right disconnect. And I can make this part my ketone, simple acetone, and then disconnect the rest of this and make it a bromide. I can now make a Grignard reagent from this, react it with acetone to get this compound, work it up. However, the first thing that should strike you is, oh, Grignard reactions really love to react with carbonyl groups. I have a carbonyl group on this carbon. I can't do that. I can't make a Grignard reaction from this molecule. Okay? So if that was our synthetic plan, this route will not work. Carbonyl group is incompatible with a Grignard. So it sounded like a good plan, but what we can do is we can take this compound. We want to get to here. What are we going to do? We're going to protect that carbonyl group. We will react it with 1,2-ethane diol, or 2-hydroxyethanol, whatever you want to call it. We're going to react it under slightly acidic conditions and make this compound. Now, if I want to make a Grignard reagent, that becomes highly basic conditions. I can make my Grignard reagent quite easily. Under basic conditions, this is very stable. Just going to sit there. Nothing's going to happen. Then we can go ahead and do our Grignard reaction. And that just goes to this compound, which we finally work up to get here. Okay? So our initial thinking was, this is not going to work directly, but we have ways of getting about it. We can protect it. We talked about a little earlier about how we can protect alcohols. Well, now we have a way to protect carbonyl groups. Now we want to be careful. We can easily protect the carbonyl group of aldehydes and ketones. It doesn't work as well for carboxylic acids, esters, and amines. They're not as easily protected as carbonyls are in aldehydes and ketones. Here's another reaction. This is a thiol. We've replaced the oxygen with a sulfur, and they act a lot like alcohols. They're even better nucleophiles than simple alcohols. And this will react much like an alcohol, and we end up with what we call a thioacetal. How many people know what the thio means? You should start to realize thio means sulfur somewhere. Okay? So thio, this is a thiol. It's the sulfur equivalent of an alcohol. We've replaced oxygen with sulfur. And a thioacetal tells us that it's like an acetal, only we have sulfur instead of oxygen. We have different ways of making this. Notice here we're using some protic acid. Down here we're using a Lewis acid. This actually has the same effect. This Lewis acid coordinates with the oxygen and activates the carbonyl and allows this reaction to go. This provides us with another way, and I don't want to get into this too much in terms mechanistically, but we can reduce this functionality. We can reduce it with hydrogen and what we call Raney nickel. Raney nickel is nickel that is kind of infused with a whole bunch of hydrogen. It's put into the interstitial holes in the metal, and it also activates it and allows this to react with hydrogen, and we completely reduce it to a CH2 group. And this provides us with a method of reducing a carbonyl or a carbonyl and an aldehyde or a ketone completely from C double bond O to C bonded to 2 hydrogens. So we completely reduce it. The next thing I want to talk about, and we're going to get into some board work, and I want to keep track of time here because we do have a quiz, and it's going to be a simple quiz. Nucleophilic nitrogen. Nitrogen reacts with aldehydes and ketones to form these things called imines, these things called enamines, and right now you're looking at that, and I'm sure some of you are saying, whoa, this looks difficult. So let's step back a minute. Primary amines form these things called imines, and an imine is just nitrogen with a double bond. It looks a lot like a carbonyl, okay, but we've replaced the oxygen with a nitrogen, and nitrogen being trivalent means it will have something else bonded to it. So those are what imines are. Enamines, simply we have an alkene, and there's an amine that's attached to the carbon-carbon double bond. We call that thing an enamine. So how do we get there from ketones? Well, we're talking about nucleophilic addition to the carbonyl group. That is the first thing. This is our general reaction of a nucleophile. We've gotten to the point where we're accepting that nucleophiles often have a proton attached to them, and that adds to the carbonyl group. The nucleophile adds to the carbon. The proton ends up on the oxygen, and we end up with things that look like this. And we already talked about how whatever this product is may or may not be stable. So this is a case where we're just reacting carbonyl group with a nucleophile. In this case, our nucleophilic group is everything except for one of the protons. That goes on to the carbonyl carbon. There it is there, right? And the other proton adds to here. This thing reacts further. That's all we have to, if we can get there, and we look at that, and we should look at that and think, that looks a lot like a hydrate, or it looks a lot like a hemiacetal. This looks a lot like a hemiacetal, except for instead of having an alkoxyl group there, we have that amino group. So it looks a lot like a hemiacetal. It will react further. The difference is a hemiacetal reacts further by having another molecule of alcohol reacting to it. So it is some alkyl group with an OH attached to it. Here we have an alkyl group that still has an NH attached to it. So this is a lot like a hemiacetal, reacts further, but instead of reacting with another molecule, it could undergo a reaction kind of with itself. How does this happen? So we've already accepted that we can get from, I'm going to do this. This is not the same as what's on there, but I'm kind of, as I look at things, I realize instead of using R, R prime, and R double prime, I'm going to start trying to put actual chemical groups in there. I want you to realize that most of the time these are general reactions. I'll talk about it, but I find it easier to follow if I use pH and CH3 instead of R and R prime. So we're going to react this, and I'm going to react it with CH3, CH2, NH2. Realize that that is equal to it's just ethylamine, ethylamine, okay? So it has a lone pair of electrons, and we can go do this, and what I'm going to do is get rid of all the cabbage in the middle, and we're going to get right to this. Okay? That is our simple, we all are equipped to get from there. Now, the other thing we have to realize, this is under acidic conditions, so we have proton carriers floating around. We have lots of things that can carry those protons around, and in fact, amines are very strong bases. Our proton carrier is very likely to be a protonated amine. But once we get there, we can protonate things, and I can protonate this, or I can protonate that. If I protonate this, we're actually going to end up back here, okay? And that's fine. If we protonate that, we end up back here. That's not getting us forward. We can always go backward. We also always realize this is reversible. Okay? So if we protonate that and we end up back here, don't get too upset. We say, well, let's try protonating something else on this molecule. What else can we protonate on this molecule? Anybody see another atom we can protonate? Everybody should be zeroing in on one atom. What is that atom? Oxygen. Right. We can protonate the oxygen. Now, that's going to make us happy because we're going to draw our next structure and we're going to see something that makes us happy because it provides us with a way of moving forward. And what is that thing that makes us happy? Look at that. We have H2O attached to something that, right? We have to form water. Now we have a way of making water. That's going to make me happy. I've now found an easy way to throw water off. If we throw water off, we end up with positively charged carbon, perhaps. But there's other ways we can do that. And there's lots of ways we can move forward. One way, let's just get rid of it. But I'm going to get rid of it this way. I'm going to push it off with the lone pair of electrons from that nitrogen. Okay? And when I push it off with that lone pair of electrons from nitrogen, I end up with this compound, PHCN ETH plus CH3 and H2O. I'm going to put my H2O in a box because that's one of our products. Okay? That's fine. I have this thing where protons jump on, protons jump off. So we have something that's going to act as a base. There's lots of things in there that can act as a base. Something is going to just simply pull that off, and we end up with our product. Now this is actually, I'm going to start from there again. And this is one of the areas. What if we did this instead? pH, C, and, oops, I'm sorry, this is O, O, H, H plus, CH3, N, ET, H plus. There's another thing we could have done. I could have done the same thing, and instead of pushing it off, I could have left it, and instead of getting this, I could have had a resonance structure where the positive charge was on the nitrogen. And if you guys did that, I'm sorry, where the positive charge was on the carbon, and we just had a nitrogen-carbon single bond, if you did that, I would be fine with that. That's fine. There's lots of ways to do things. Another thing that someone might do is throw their base in here, okay, and do everything at once. And that will also lead to this same compound with the water in the box and our protonated base. I forgot that here. Okay. And the only difference between this and this, if we want to think elimination-wise, this would be equivalent to way back last class. This would be equivalent to an E1 elimination, and this would be equivalent to an E2 elimination. As it turns out, it's going to depend a lot on your conditions, how many things you have that are basic around, and you have enough basic things that both of these things are probably occurring. Okay? So if you went the way up top, you're going to get it right. If you went this way, you're going to get it right. Okay? So that's where I don't want you to get held up in anxiety because you don't know how to go forward. The best way to move forward in organic chemistry, try something. Okay, do something. Do something that makes chemical sense to you. Move a proton, add a proton, remove a proton, form a double bond, learn how to push your arrows, and you end up getting to the right place. So there's more than one way to get here, all of which are, you know, more or less correct. It will be condition dependent, but you're not going to, even if conditions were such that I said it absolutely had to go through this mechanism, if you use the other mechanism, it's not disastrous. You get to the same product. It's going to be 90% on that question. If it were a case where I was able to say, absolutely, I know it goes through that mechanism. This is not one of those cases. All of these mechanisms would be valid. So now when we go through here, just what I did on the board, exactly the same, except that we kind of went to here because we already knew how to do that. And notice then they go from here, they protonate it. They went through the mechanism as I did initially because that's probably the more correct mechanism. But we do have lots of strong base around. We have, at the beginning, we have lots of strong base because we have lots of ethylamine. Ethylamine is a strong base. At the end, we have less ethylamine, but as it turns out, these things, and it can even, this equilibrium is going to be there depending how much acid we have. Okay, so there's lots of ways to get there. The nice thing about this reaction, remember that H2O we put in the box? We can go in the opposite direction. We can start from an imine, throw in a whole bunch of water, and we're going to end up going back the other way and spit out our carbonyl compound. Okay, and that was at the beginning of the lectures on this chapter. There was one of the reactions where we formed something that looked like an imine. Remember, we reduced a cyano group, a nitrile, and we ended up with something that looked like this. And that's how we got from there to the carbonyl compound. So what we're going to find next class now, we can do this same reaction with things that look like primary amines. This looks a lot, this is a primary amine. It doesn't look like a primary amine. It is a primary amine, and we get an imine. Well, what if we replace that R group with an OH group? Then we have something called hydroxylamine. It's hydroxylamine. It acts a lot like a amine. Now, what may happen in this particular reaction, you may decide to use the oxygen for the nucleophile, and that would be an unfortunate choice because you could end up with products that look like they might get there. But what do we know about the nucleophilicity of oxygen versus nitrogen? Nitrogen's a better nucleophile than oxygen compounds. So this is a stronger nucleophile than this. Okay, and we get something that looks very much like an imine. We call it an oxime. The next thing we're going to get is hydrazine. This one's nice because it doesn't matter. We have two nucleophiles in this molecule, but they're both the same. Hydrazine is used in rocket fuel. So we form something that looks very much like an imine, but instead of an R group, we have an NH2. This is called the hydrazone. That's actually convenient because it leads to stuff we can do further, which we'll see next class. Enamines are different, and this is the last slide for today. Enamines are different because here we have a carbonyl group. When we react with a secondary amine, the compound we make may be more reactive if there's a hydrogen on what we call the alpha carbon. Okay? And if that's the case, we end up getting to this enamine. We'll talk about that next class. It's also a nice reaction that we can progress to logically knowing mechanism and how to push arrows.